We're continuing with a worksheet that's mainly about the end of the story, or at least the story that I'm going to tell, about applying differential forms to electrodynamics. There's one other very cool way that forms, there's sort of one big law that we haven't really talked about that look very cool in the language of forms, but we need one other operation. And I'm going to use this as an excuse to do something more than we really need, because it's actually a very useful operation in general in forms. And that's called the interior product of a vector and a p form. Okay, so over here, I'm going to remind you that if I have a one form, alpha, remember the picture of that, maybe in 3 dimensions, was these stacks, like parallel sheets. So this might be like, if this is the x direction, then this is a picture of alpha equals dx. And the job, its job was to, or one of the ways you can think of that is that it eats a vector, let's say u, and gives you a number just by how many sheets does it go through. And so here alpha paired with u would be 3 in this case, that it crosses three different layers. And so we already know that if you have alpha and u, they pair to get together to be a number. Well, what if you had, and then let's see, let me remind you of one other thing. If you had like beta is a 2 form, then that's the kind of thing that's like a honeycomb structure made, you can think of it as kind of made out of 2 of these guys. So you've got sheets maybe going this way and sheets going this way, and that can eat 2 vectors. One of the things we used this for was we imagined sort of fluid flowing in this sort of direction between the sheets, and as a sort of tubes of flux. And then if you take 2 vectors, we created, like u and v, we created the parallelogram spanned by those guys, and the number of tubes cut was how beta eats both u and v to get a number. So what if we only had beta, a 2 form, and u? What would we get? Well, we'd get something that's kind of beta of u and an open slot. And so this would be a machine that would beg to have one more vector put in, the v, and then that would create a number. So in other words, what we've created here essentially is a one form, something whose job is to take one vector and produce a number. So here, for example, let's say the green stuff is fixed, the beta is fixed, and the u is fixed, but I don't have the v yet. As long as I just put in one more vector, then I can form the parallelogram and get a number. So somehow the combination of beta and u, we should be able to produce out of that this kind of picture that is ready to just take that extra vector v. Okay, so that can get a little hard to visualize about exactly how that should work, although I'll come back to the picture in a minute. But algebraically, there's actually a very elegant way to define this. So I'm going to kind of just give the algebraic definition without an incredible amount of motivation, and then see how that, at least in some cases, actually does have this kind of picture associated to it. So here's what we do. We have 3 rules for the interior product. This here is a little Greek I. It's an iota. There's many notations for the interior product, but this is one of the popular ones. And what I first want to do is define the iota with a vector, and here it's going to be one of the basis vectors ei, acting on one of our basis 1 forms dxj. Well, the idea there is it's supposed to replicate a 1 form acting on a vector. And there, if I had dx and I had a vector in the e1 direction, for example, then I'd get 1. If the vector was in, I guess I can actually use the real pen for that, if the vector was in the e2 or e3 direction, then I'd get 0. And so that's what this is about. We use this symbol called the Kronecker delta, which just gives 1 if I equals j or 0 otherwise. It's basically the identity matrix. And I just say that the interior product of ei with dxj is going to be either 1 or 0. Okay. The second thing is with all this stuff is we just want this to be linear in both arguments. If I double this, if I double the vector, I get double. If I double the form, I get double. If I add stuff in here or add stuff in here, I get the sums distribute out. And we'll use that. We'll demonstrate that in a little bit. But here's the crucial thing. Here's how it acts on a higher degree form. If I have a wedge of two forms together, then it actually, the rule is very cool. It actually acts just like the product rule for derivatives with exactly the same rule for the sign. So you have one term where you're interior producting alpha with u, and the other one where you're interior producting beta with u. Now let's think about what that means about degrees. This thing says that interior product in one form creates a function, a very simple function, just 1 or 0, constant function. So that's an example where the form degree goes down by 1. Well, let's suppose that that worked, that IU of alpha is 1 less degree than alpha, and IU beta is 1 less degree than beta. Then the degree of the whole thing, well, I've got something that would be the degree of alpha plus the degree of beta. That's what I started with, but minus 1. And here, the same is true. It's going to be minus 1. So that says that for all forms, it's going to take the degree down by 1. And that's exactly what I was trying to indicate here, is that I took u and beta, and putting those together and leaving an open slot produces, from a 2 form, it produces a 1 form. Now we've just got this new notation for the same idea. Okay, so let's look at some calculations here based on these rules and see if it seems to indicate this, or be consistent with this picture. Okay, so I e naught of dx wedge dx1. Okay, let me just copy that and paste it here. Okay, so what's that going to be? Well, I can use this rule. It's going to be I e naught of dx naught wedge. I think I need to make this bigger so I can have some. There we go. Okay. Wedge just dx1 alone. I'm not going to do too many tedious calculations. Don't worry. I'm going to try and sort of shortcut some of the more tedious stuff. Now minus, because alpha is a 1 form here. Dx naught is a 1 form. So it's going to be minus dx naught alone wedge I e naught of dx1. Okay, now one of those things is going to die. The I e naught of dx naught, that's 1, and so we get left with a 1 dx1, or 1 wedge dx1, which is just dx1. And then this one is actually going to die, because I e naught of dx1 is 0. So all this does is it strips off the dx naught. As advertised, it took a 2 form and produced a 1 form. Okay, let's see if that fits with the picture over here. Okay, let me redo the picture. So suppose this picture, let's do it in just in R2, because it really is almost the same in any dimension. In R2, here's a picture of dx naught wedge dx1. So again, because I'm so used to, in these recent ones, I'm so used to starting with 0, I went ahead and started with 0 here, thinking of this as space-time, but it doesn't really have anything to do with space-time versus space. So here's dx naught wedge dx1. It's just a grid. It's just the dv, the quote volume form, or dA in R2. And I take that and I interior product it with this vector e naught. Well, so what is that supposed to produce? It's supposed to produce a form so that if I took another vector, it's supposed to be a machine so that if I took another vector in here, call it v, then, and then I made the parallelogram, oops, not very parallel there, with the e naught, then it would produce the area of this guy. Okay. Well, the area of that is, because that's dx naught wedge dx1 acting on the e naught and the v. The area is just base times height, which is 1, because we picked that to be e naught, just a unit vector, times, and what's the height of v? It's exactly how many bongs of the bell there would be if I took the dx1, which is going in that direction, and acted on v. And so that says that the machine I've actually created, it should just be the dx1 machine. So it really comes down to area equals base times height. If I set the base to be 1 unit in the direction of E naught, and then I say what other information do I need to provide, it's the height information. It's exactly dx1 waiting to eat some other vector coming in. So that's what this is saying. It's saying if you take the area form and you say one of the legs of one of the sides of the parallelogram is defined to be E naught, then the machine that's going to tell me the area is just the height machine, and dx1 is just the machine that records the height of a vector. So that's saying there's a geometric interpretation with this that matches this kind of formal algebra. Okay. Now, what about if I just change this all to E1 of dx naught wedge dx1? Well, this is just going to be E1, and then this is going to be E1. And now notice it's the other thing that dies. Now it's going to be dx naught. So the other one is left standing, but it's going to be with a minus sign. And that's about the orientations. I was playing fast and loose with orientations here because it happened to be that we got a positive sign. But if you put it in the wrong place, or the opposite order, basically, then you have to watch out with signs. Okay. Then, for example, here, DIE2 of this guy, let's do one more calculation just straight up by hand, and then we'll do some more general ones more efficiently. Okay, how would we do this? Well, we could use this rule where the dx1 is the alpha, and so let's do that. So that's going to be IE2 of dx1 wedge the rest of it, plus or minus. Well, it's a minus because this is a 1 form, and I'm switching the IE2 past a 1 form. dx1 wedge, actually let me make it fit better, and then the IE2 of the rest. Oh, now that's also a wedge. Okay, so I'm going to have to expand that out. Well, first thing, IE2 of dx1 is going to die. Okay, so that's just not even going to come in. So it's going to be minus dx1 wedge IE2 of dx2 wedge dx3. Oops. And then, ooh, and I need this in parentheses. Okay. And then minus, because I'm commuting the IE2 past the dx2, dx2 wedge, and then IE2 of dx3. So with effort, let's go over a little bit here. Oops. Let me adjust things just a tiny bit here. Okay. IE2 of dx3. I'm trying to keep these both on the screen at the same time. That might be stupid. Let me go up here. Okay. And a lot of this is going to die. So we already saw the IE2 of dx1 dying. The IE2 of dx3 is going to die as well. So all we get is minus dx1 wedge dx3. So notice what's left is the thing that didn't match. So this IE2 is basically eating the dx2 part. And it's a minus sign because this was in a place that the IE2 had to skip over one thing to get to it. Okay, and we'll see that that's a very general rule. Okay, so we're getting the idea of what it does, at least with the basis vectors. What about for an arbitrary vector u? This is a good time to stop the video if you want and try and do this yourself. This is where we start using the principle that this is supposed to be linear in the argument, in the vector argument down here, as well as linear in the form argument. Okay, so let's look at this one. I'm going to steal it from down below, right here, and then just talk about it. I won't do it live. So u is going to be a combination of u0, e0 plus u1, e1. Again, if our coordinates happen to start, our indices happen to start with 0, which they do in space-time. And I'm going to act that on dx0 wedge dx1. Well, by definition, that's supposed to be the coefficient u0 times I e0 of this form, plus u1 times e1 of this form, plus ... all the e2 and e3 stuff. But now we should have realized that if you have e2, e3, etc., and these are dx0, dx1, that's going to be 0. So you only get these two contributions. I e0 of dx0 we've seen as dx1, and I e1 of dx0, dx1 is negative dx1. So again, it's just kill the one that matches and put in an appropriate sign based on how many things you had to switch. Very, very standard kind of forms manipulations. So it ends up being u naught dx. Oh, this is a dx naught. I think I had this wrong. There we go. So it's a combination of the dx naught and the dx11 form, the things that were the building blocks of this guy, and with u naught and u1 put in. Okay. This is something we could go back to this picture down that we had here and put in a slanting vector u. This is, again, the area form in 2 dimensions. And we could talk about how this is really encapsulating the idea of, again, area of a parallelogram is base times height. But it's a little more complicated because this is going to be a slanting vector. And I don't want to worry about that right now. Okay, what about, just a little harder, is if this is dxi which dxj. I just want to warm us up for the case. Yeah, I know that. I just want to warm us up for the case where we're going to have like a lot of weird indices and we have to deal with that. So let me just change this to an I and this to a j. Actually, you know what? I have this pre-made and it's going to be faster to do that. Let me go grab it from below. Okay. And it's just an issue of bookkeeping. It's extremely similar. Here, I really do have to be prepared to use all the components of the u vector. So we express it as a sum of uk, ek. So k is going to be a dummy variable, and I guess I could put a subscript k on the summation. Now, luckily, pretty soon that summation is going to die because there's only 2 things that are going to contribute. It's only where ei, because that matches this guy, and ej, because that matches this guy. It's only those things. So we're going to get whatever coefficient was in front of ei and whatever coefficient was in front of ej, matching these guys. And again, it's going to be very similar. Just ui dxj minus uj dxi. If that starts to look sort of cross-product-ish, it should, because this is very much tied in with things like the cross product. But of course, the idea of lots of minus signs and sort of permuting indexes shouldn't be at all unfamiliar by this, by like, what is this, the 30th in this sequence of videos, if you've come this far. So what about if I have a fairly general basis p form? So here I have to have double subscripts because it's not just necessarily dx1, dx2 through dxp. It's j1 is any number, j2 is any number that's, let's say, bigger than that, so I have a standardized order, then j3 all the way up to jp. So it could be dx2 which dx7 which dx15 which dx31 in 47 dimensions. And then I've got one other index, I, that tells us which basis vector we're actually taking the interior product with. I should advertise, if you want to skip to how this applies to electrodynamics, you don't really need anything beyond what we've said with the 2 forms, okay? But this isn't super hard to do. Okay, so let's see. There's going to be 2 cases. If the EI vector, if that index, that dimension or direction doesn't match any of these guys, what's going to happen? Well, it should be pretty clear that that's going to be 0. That was sort of what we were seeing with these previous calculations. If this doesn't have anything to latch onto, I'm going to expand it out using this rule multiple times, and it's just going to come down to the zeros here. So that's not going to be particularly interesting, but it's really nice to know for the next calculation. Okay, so let's suppose I is one of these things in the set. We need to be careful about the sign because we're going to have to count number of switches. So let's see how to do that. Again, a good place to stop the video right now if you want to try it yourself. But these bookkeeping issues can be hard to do if you've never done them before. So let's look at this. So here's how I want to set it up. I'm going to set it up so that, I have to make that wider again. Let's set it up so that we make very clear the connection. Just saying I is in this set is pretty vague. We'd like to actually say, where is it? Which, if it matches the 2nd or the 5th or the 15th one in this sequence, it's going to matter, especially whether that's an odd or even number. So here's, let's say j sub q is equal to I. So whichever vector this is, it happens to match the qth entry in this sequence, where q is some number between 1 and p. So now I'm going to use my my basic rule and a little bit of switching around. So IEI, I'm just expanding this out. I'm saying very, very explicitly it goes from J1 and then it hits JQ, and I wanted to make sure I had the ones right around it, before it and after it, and then up through JP. The reason for that is I'm going to take this and I'm going to switch it over Q minus 1 things, which gives a sign of -1 to the Q minus 1, and then I'm going to put that in the front, and I'm going to realize that's DXI. because I was equal to JQ. So I'm signaling that out specially and putting it in front so I can use my rule, the sort of product rule analog. The rest of it is just what we had before without the dxjq sitting there. Okay, so now the product rule says it's going to be IEI acting on DXI, wedge all the rest, plus DXI, wedge IEI acting on all this rest of this stuff. But the whole point is there's no match anymore. From this part, if we believe my argument there, then that's all going to die. So we actually only get the one term. IEI DXI is just 1. So you just get -1 to a power, plus or minus, all the rest of the dx's. That's exactly what we were seeing up in these examples, is that like here the dx2 died, we left the rest of them, and it was just a minus sign or a plus sign depending on exactly how many switches there were. So that makes it official. It's plus or minus the rest of the dx's that weren't matching, and the minus is how many switches would you have to do to get this vector into the position that it matches with the dx's. Okay, so that's a good place to stop this video. We're going to explore a little bit more that's kind of cool about the eyes, and then we're going to go back to a very simple use, not nearly so complicated with all these indices, in electrodynamics.